Now that we've laid the groundwork for some of this, we're going to talk about elastic solutions to soils, deflections, and stresses. I mentioned the last lecture that we're going to use what we're going to use for this course and next for conceptual purposes is the Moore Coulomb failure theory with elastic, purely plastic deformation. What that means is this, is that we start with zero, we go up in an elastic way to a certain point, at which point we say it fails, and then it will take no further, some maximum stress, and then it makes none. It will not basically go beyond, it just deforms. It doesn't increase the stress resistance. It won't take any more stress. That's what we're going to assume, and that's going to govern how we approach different problems. The way that soil mechanics, however, up until in a finite element model, you will see the finite element model is one of the beauties of finite element analysis is that it's able to go from one to the other without, or any other soil model it might pick, without having to stop and change everything. Well, it does change quite a few things, but without using the same model, basically. It could go from one to the other. Traditionally, though, in soil mechanics, we have not had the luxury of that. So basically, our methods break down into one of three things. They either are elastic methods, they're plastic methods, or they're methods based upon consolidation and rearrangement of particles. And we're going to talk about that shortly, but for the moment, let's start with the elastic models. The elastic models are very useful for many things, particularly when the deformations are relatively small, and frequently the elastic models give us pretty decent approximations for what stresses are in the soil that we induce in them as we put stuff on top of them. The theory of elasticity can be used, and has been used for a long, long time, to estimate deflections and strains in soils. And one of the things that we're going to try to integrate together is the fact that we can use theory of elasticity for both. If you recall Hooke's law, you have something which is equal to the force is equal to the spring constant times the elongation. F is equal to K delta or whatever. Well, that tells you two things. First of all, it tells you what kind of force, and if you had an axial member, you divide by area, you get stress. If you divide K, in that case, by area, you would get modulus less. Well, you would get a kind of a modulus less. You can bulk modulus or something like that, which we'll talk about that too. You get that, but in both cases, you're dealing with both. We talk about you're estimating stress and deflection using very much the same kind of using the same model. A few things about that: they're highly nonlinear, and we usually restrict elastic solutions to relatively small strains and deflections. And we're not going to talk about strain softening defects. I passed over those the last time, and that is a very topic of growing interest in soil mechanics and geotechnical engineering. What we do in the kind of solutions we're going to look at now is we apply it to a semi-infinite solid. Basically, that's how we envision the soil. The soil has a surface, and it goes infinitely this way and this way, but not this way. So we have a semi-infinite solid. And if you would, if you were, it makes intuitive sense, and I always invoke that very cautiously, to say that if you apply a load somewhere, a finite load somewhere, the further away you get from that load, the less of an effect you're going to see in the soil. And that's exactly the way it works. Now, the math may be a bear, but it works that way. And the other thing is for just, those loads, you know, we do talk about point loads, but for most of our loads are distributed. And then the other thing that is the relative flexibility of the foundation relative to the soil. We can also assume, and this is particularly important for deflections, we can assume that the foundation is either perfectly flexible relative, in other words, that it maintains the load, the uniform load, while it, you know, deflects into some kind of bowl, and then, or we can assume that the foundation is rigid. This is really rigid, and the soil has to do all the deflecting. You get different results, particularly again when we talk about for both stresses and in terms of deflections as well. Now, obviously, again, if you really want to nail this problem, you would use something that would take the, you know, neither one of these assumptions is really accurate. Some soils are, you know, very soft, and the foundations are, for all intents and purposes, rigid. And then some soils are relatively hard, and the foundation could be flexible. But if you want to do a rigid, and you know, try to figure out which is which, you could you would need a more sophisticated model. And that's another place where FE becomes very useful. How do we implement this? The most common method is Boussinesq theory, made by the Frenchman who came up with it. It's based on a theory of elasticity. It assumes a homogeneous isotropic material, which should already arise suspicion in you. The original equations he came up with derived semi-infinite solid. I talked about that. Original equations describe a point, and then it can be applied to various foundation shapes. It can be used also for both deflections and stresses. One of the things that you see in a lot of Boussinesq solutions is that they will assume values of Poisson's ratio to keep them simple. In our cases, we're going to, that's because one reason, stresses that do this way, Poisson's ratio says they also have this way, and in many cases, shear stresses as well. So in our cases, we're going to focus on vertical stresses. And we're going to come back to, you know, some of the other ones are horizontal stresses. We're going to come back to horizontal, actually, a little bit later in the course. Westergaard theory is similar to Boussinesq, except that no lateral deformations of the soil. In other words, it assumes that the soil is semi-infinite, that because the soil way out here doesn't move, it confines the soil in here. It is used in soils of alternating layers of materials, which something Boussinesq doesn't do, and it is used extensively in airfield pavements. I'm not going to talk about that. Newmark's method is an adaptation of Boussinesq theory for structures that do not have a simple shape. It was developed actually by Nathan Newmark, a name you've probably run across in mechanics of materials. He taught at the University of Illinois. However, Newmark's method is a classic example of the fact that the prophet is not without honor except in his own country, in the fact that Newmark's method is more popular in Europe than it is over here. And I've taught it, sometimes I've taught it, and sometimes I haven't. And I'm not going to teach it in this course. Newmark's method is a good method. It's the most flexible method if you know how to use it. But students have a lot of conceptual issues with Newmark's method. Last but not least, the 2-to-1 method. It's an empirical method for stresses only. To estimate structure-induced stresses under the center of the foundation. It cannot be used for side stuff like Boussinesq theory can. The FHWA pushes it, and the results for practical purposes can be, it's easy to compute, and the results for practical purposes can be very useful. We're going to talk about point loads, line loads, and strip loads, which are an extension of the Flamont, which Voigt explains in detail, rectangular loads and circular loads. The chart analytical solutions can be combined because of superposition. This is very important. As you probably are aware, or if you're not, you're going to be, rectangular loads for inelastic theory is path independent. And what that means is that you start from 0, for example, and you move anywhere, as long as you're within the elastic region, no matter how you get there, in other words, if you load, unload, all this stuff, as long as you're in elastic region, you will always get to the same place. That, in a crude way, is path independence. Once you get past the elastic limit, what deflections and stresses you get depends on how you got there. That's path dependence, and that is a mark of plasticity. That's one reason why plastic problems are so tricky. So that's when I talk about path independence and path dependence, that's what I'm talking about. Solution methods, equations, usually. For simple methods, they're okay. For more practical cases, complex cases, they're generally not practical, and you're going to see that big time. Seriously, big time. Mistakes are common in literature on the internet, so be careful. The charts are more reliable from that standpoint. Charts have traditionally used, they have accuracy issue. You have a computer program, make sure it's right. And of course, Newmark's graphical method, which is another way of checking things if you're proficient. We're not going to cover it in this. Let's start with Boosin-S point stresses. Now, point load, and this is straight out of Voigt. If you apply a point load anywhere, you will get, it shows you the ZZ stresses, and notice his axis. If X and Y are all in this plane and Z is this way. The vertical stresses are ZZ. That's a fairly simple equation, and there are some simplifications that have taken place. Notice that now there is about as many ways of stating these equations as there are books. Voigt uses the Z and R approach. Z is the distance from the load down to the plane of this, and R is the distance from here to is the triangle distance from here to here. In other words, this forms a triangle. This is the hypotenuse of that triangle. Obviously, if you're directly below the point, then Z and R are the same. Obviously. Well, I think it's obvious. But you also can get radial stresses. He's using cylindrical coordinates here. Radial stresses, tangential stresses, R and theta, and then you get shear stresses as well. So you get all 4 types of stresses there. There are a couple of just below the point load. He actually does simplify this equation to get this one. And also he discovers that your shear stresses go way directly underwards, under the center load, which kind of makes sense. And your hoop stresses are equal to this. So this is the special case under the center, which is where you get your maximum stresses anyway. Once you get away from the center axis, your stresses will go down. Now, you will note that when Z is equal, let's look at these, for example, make it a little simpler. When Z is equal to 0, all these stresses blow up. That makes sense because true point loads, loads with an infinitely small footprint, just to try to use an expression, don't really exist. And if they did really exist, you don't the results are bad. You have to be careful about using this theory, point loads. You can apply, in some cases, if the foundations are relatively small, point loads are a nice approximation, and they're easy, and the equations are a lot easier to use than what you see elsewhere. But the Bussinet, point loads are singularity. We have the same problem with the deflections. Have the same problem. Deflections assume, for r, as r approaches 0, that radius approaches 0, I think it blows up for deflections too. We don't use these often because the singularity, because usually if we're interested in the deflection issue, our interest is normally restricted to the foundation itself, right under it. And so we don't normally worry about the deflections of areas under the foundation. And since it blows up, we don't use the deflection equations very often with point loads. So we have an example. Given the Bussinet point load illustration, the point load of 45 kilonewtons, and let's talk about 0.3 meters directly below the point load. Find the additional vertical and shear stresses created by the point load. Z is equal to 3 meters. R is equal to x squared plus y squared because v squared is square root of all that. Amazing, 3 meters. Why? Because x and y are 0. R is equal to little r is equal to 0. So we just plug and chug. We plug and chug the equations, and we get 3 meters. The stress is 2.387 kilopascals, and the shear stress is 0, as I said. But directly below the center of the load, the shear stress is 0, and that's something we're going to see repeated more than once with these types of stresses. Now we come to line load stresses and, by extension, strip load stresses. And as Verroy explains, the French scientist Flamand came up with these. And they're really an extension, a two-dimensional extension of point loads. And they have the equations. I've seen a number of ways of expressing them. Verroy's approach to this is the simplest from a math standpoint. The tricky part is getting this angle and this distance right. That's really kind of the problem with this particular one. If you do them in a strictly Cartesian coordinate system, the equations are a mess. If you do them in a polar form like he does here, or cylindrical more accurately, then the equations are simpler, but the geometry is a mess. So he's got this laid out this way, and I'm going to stick with that. These are very useful. We're going to see these again, particularly when we get to retaining walls. The problem with line loads, as is the same problem you have with point loads. They have an infinitely narrow footprint, and as a result, you get a singularity at the load, which makes them of some utility for stresses and virtually none for deflections, as Verroy points out. Strip loads basically are line loads with width. And basically, again, Verroy opts for the geometrically simpler approach. I mean, the mathematically simpler approach, but the geometrically, and the fact you have to compute these two angles to any different point. Now, obviously, he points out the fact if you go straight down the middle, the angles simplify. You can seriously simplify the expressions he's got here from here down to there, and that's nice. These are more useful because stuff has real width, and infinitely long foundations are an interesting topic, and we're going to see them again and again and again and again and again in this course and the next one. We're going to, and again, with infinitely long foundations, you have a load that's distributed, obviously distributed this way, and it's infinitely long going in and out of the paper, so to speak. These are more useful, particularly if we apply a theory of elasticity to them. Down here at the bottom, he's got a little bit different way of writing these things. These are, but not, one of the things I want to note is that not only does he give you the equations for the vertical loads, but also the horizontal ones. And we're going to see that when we get to retaining walls, because if you have say a roadway or a railroad or whatever next to a retaining wall and you push down this way, it's going to push against the retaining wall this way. And those loads are significant, or can be significant, let's put it that way. And usually we use some type of variation of this to compute those stresses. We also have chart solutions for those. I believe that's from your Soils and Foundations manual. I personally prefer the math, given the fact that we have, calculators and spreadsheets now. I'm not real fond of these. They're hard to read, particularly as you get close to the foundation, which is where obviously interest is. They're very hard to read, so I'm not really too fond of them. Not all foundations are semi-infinite. They have squares and rectangles. These are a little hard to understand. The Boussinesq solutions traditionally take it off, and this is called a Fadum chart after the researcher that first published it. We have basically what it is this: if you've got a rectangle and you look under the corner of that rectangle, then you have two things. The rectangle has an x dimension and a y dimension. And if it's a square, x is equal to y. How about that? So therefore, we define two quantities. M is equal to x over z, and n is equal to y over z. And it doesn't really matter which way you do it, as long as you're consistent in the way you do it. Again, we got superposition going for us, so it shouldn't really make any difference, but you should get the same result no matter which way which you pick for x and which you pick for y. As long as you're consistent between the two of them and you're doing multiple foundations, you're fine. Then, once you do that, you use these values of n, and then you've got different values of m all the way up to infinite n. That would be a strip load. And if you know n, you know m, you can compute the influence value. Now notice that the influence value doesn't go past 1/4. The reason why that is because this is if you were dealing with a foundation, you want to do it on the center of the foundation, then the center of the foundation, each of the quadrants is only 1/4 of the load. You add them all up, you get unity. So for a very large foundation, obviously a small foundation is going to be less than that. So that's how you use those. You pick an N, you have an M, you get that. Now, using the same notation, these are the equations that develop the Fadum charts right here, using the DM7 notation, which is where that chart came from, the N and the M. If there are two conditions. This is a little tricky. The literature varies in the way that it presents this type of thing, but you see these equations are not easy. I will tell you though that I use these equations in spreadsheets when I'm grading homework. And the reason why I do is because I'm trying to eliminate or reduce chart reading errors for the answer. Because in a problem like this, you have, with all the assumptions, you have one right answer. And I want to eliminate the chart. So I use these equations in spreadsheets to, because otherwise they're a bear to do by hand. Once you get this down. I will mention also that I have another web piece which goes into the development of these equations and their use. And actually I construct my own Fadum chart on that particular website. And there's also other little aids and spreadsheets and whatnot that you may find useful. So I would suggest you check that out too. One of the tricky parts about the superposition is is how to use superposition. The corner is an interesting point, but it's not necessarily the most interesting point. For example, the center is more interesting. And so the center, if I had 4, it's like this. If this A were in the middle and all 4 of these rectangles were the same, I would get the center load, the center stress for it, depending upon how deep I went. But one of the things you can do with rectangle loads is use superposition to determine a load either away from there, if you've got a funny thing with a corner, or if you've got a situation where you've got 2 different uniform loads. You can also do it that way. And we're going to see that. I would suggest that you would study this particular chart very, very carefully and see how it works. And we're going to give an example of doing all of the above right here. This is from Verreut's Newmark example. You can see how he solves it using Newmark's method. We're going to use the Fadum charts and the rectangle solutions. There are 2 buildings. The yellow building, is 10 meters by 2 and has a load of 5 kPa. The brown building has a uniform load of 15 kPa. And what we want to do is to find the vertical stress. And that's what we're talking about with these Fadum charts. And the rectangle is vertical stress 8 meters below point A, which is not under either one of them. So what do I do? Well, the solution, and actually I can post a spreadsheet so you can see what's going on here. Since there are 2 different loads, is the best way to do it is to analyze the loads separately and then add them together using superposition. The notation is per the previous chart. The chart, in other words, this one. In both cases, it was simpler to compute a large area and to subtract a void from the area. I'm going to show you how that works. The influence for equations from the equations can also be obtained from the charts. Let me show you how to construct that. First of all, I have B and L, which are the B and L are my traditional notation we use in American geotechnics is B being the width and L being the length. And sometimes the length and the width are the same. That means you have a square. And but that's not the case here for anything. But it doesn't, as long as you're consistent with your axes, in other words, as long as you're consistent, you'll get the same result. As long as you're consistent. And in consistency, I mean consistency between, the 2 loads you're working with. If you're only working with one load at the corner, and this is really at the corner, then all you need to worry about is, B and L are arbitrary. If they're not, then the B's and the L's, the X's and the Y's should be the same. Okay. So B and L and Z is the same for all 4 of them. That's nice. Now, M is this over this. B over Z gives you M. B over Z gets you M. B over Z gets you M, and B over Z gets you M. N is equal to L over Z is equal to N, L over Z is equal to N, and L over Z equals to N, and so forth. So that's how I construct it. And I construct that from, what I'm doing is this, in a quantitative. All right, let's take the yellow building load. How do I compute the yellow? Well, it's easy. The first thing I do is consider this to be a foundation. In other words, from here, over here, up here, over here, and down. That's the full foundation. Then I subtract the void. In other words, the void is negative. The void is from here, 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 and here, and down there. In other words, all of this, subtract this, I get that. The load from that. And that's what I'm doing for the yellow foundation. I just take, this is the full load. This one is the full load of this, 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 and this. And this one is the negative load from this, 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 and this. And basically I'm saying this is the full load, and then I got something pushing the other way, which is the same as zeroing it out for that part. I would strongly suggest that that's why the pressure, for example, in the void is negative and the pressure for the full thing is positive. I would strongly suggest that you take these M's and N's and confirm to your own satisfaction that my I sub Z, the influence coefficient, is the same. And the influence coefficient, by the way, is very simple. It's the ratio of the uniform stress at the foundation to whatever stress is down there. That's all. That's all it is. That's the ratio. In fact, that particular, if you'll go back to this, you'll notice that sigma Z is equal to I times P. In other words, if this load, uniform load, is P times the influence coefficient, and you can say sigma over P is equal to I, or however you want to do it. That's I times P, by the way. Now we come, and that's the yellow building. And the yellow building yields 0.186. The brown foundation is sort of the same. The brown foundation, we start with the full load is this, 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 and that. In other words, this foundation. See, with the yellow foundation, we could ignore that. Now we're going to do it, and we're going to ignore that. So we start with this, and then and that's a common. And by the way, all the you've got common corners with those. This this full load and this load, void load, has a common corner. This load here has a full minus this right here, 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 and here. And that is the foundation with the negative load. They have the common corner, so we're all set to do that. And that's how I solve it. I have this here is this full load. There. And then this load here, minus, is equal to this load right here. I subtract the two. Notice that these pressures are different, but since since I'm subtracting this load from this one, it's the same. There are ways, I guess, you could mix them up, but the things are mixed up enough as it is, so let's just leave it. I get this, and I get 0.083 kPa. I get these influence coefficients, and I subtract this negative pressure, I get this. I simply add these two pressures by superposition, and I get 0.269, which is a little different from Freud's. One of the drawbacks of Newmark's is it's not particularly exact from a calculational standpoint. So that's how you use the rectangles with a multiple setting. Actually, you can look at Voigt solution as well. I think this is simple, and this is actually mathematically more exact than Newmark's method. Now we talk about circular structures. In the case of the flexible load, the distribution is by this equation. This is the only thing we're going to look at with circles is what's directly under the center of the circle. And in the past, I have taught use NAFAC's Alvin and Foster charts about that, and I have not been able to unearth, as of this video, the equations that Alvin and Foster used to develop those back in the 50s. And so I just haven't found those yet. So with that in mind, we're just going to concentrate on right directly under the center. And the stresses are, there are no shear stresses there, but you have radial stresses and you have radial stresses or horizontal stresses and vertical stresses in those cases. You also have another thing that Voigt goes into are the deflections due to if you have a rigid plate. Up to now, the foundations we've looked at are for the most part flexible. The rigid plate gives you a different distribution of stress under the plate than a flexible one. And I actually spend some time on that in my little web piece, and you can read that if you're interested in it. But you do get different results for the deflection, and you get different result for the stresses as well. And Voigt notes that in his stuff, and I'll note it here as well. Circular tank example. I have a 25-meter diameter circular tank. The soil is 18 kilonewtons per cubic unit weight. The water table is very deep. The weight of the tank is 6,100 metric tons, which is a metric ton is 1,000 kilos, which it comes out to 59,800 kilonewtons. Find the vertical stress due to the tank 10 meters below the center of the tank. The effective stress introduced by the overburden and the combined stresses. Here we're going to deal with two separate issues. First, we're going to find out what the tank does, and the second, we're going to do what the soil does. And we're going to, the bearing pressure is equal to 122 kPa. Voigt's equations are one of the things you're going to find out about. Sometimes they'll write these equations in terms of the total load of the foundation, sometimes uniform pressure. Voigt does this uniform pressure. That's what this P is all about. So we divide that by the area, get 122 kPa. The effective stress due to the overburden, since there's no water table, it's the total stress, is equal to 10 meters times 18 kilonewtons per cubic meter, is 180 kPa. The stress induced at 10 meters, and we just plug and chug this equation down here, is equal to 92.3 kPa. And that's just a strictly plug and chug. We see that the Z is the distance below the center of the foundation. Z plus A, which is the radius, by the way. It's not a tricky thing about Voigt. A is the radius. So instead of being 25 meters, it's 12.5 meters. So be careful. You just plug and chug, and you get 92.3 kPa. You combine that with the effective stress, and you get 272.3 kPa. And we're going to talk about how we deal with problems where we start out with an effective stress, and then we add stress to it, and we get a new stress. And we're talking about how that works here just shortly. Elastic settlement is based on the theory of elasticity. It'll, you know, for you know, we found that the elastic settlement was not very useful for, you know, point loads and line loads, but for distributed loads, yes, it is. Now, I deal with the whole issue of we're going to talk about how we deal with that, but this is the simple case. The simple case of Voigt talks about the uniform low circular foundation. We will assume a flexible foundation, and we get this deflection at the center of the foundation, where P is the uniform load, A is the radius, and E is the modulus elasticity of the soil under it, and of course nu is Poisson's ratio under it. We can estimate the we can estimate the elastic settlement. Well, now you ask, how useful is that really? Well, there have been different ways of teaching this over the years in terms of elastic settlement. The classic way of doing it is that you would use the elastic settlement for the first stage of deflection and then use consolidation and other types of settlement for the next two. In this case, there is one thing I want to emphasize, and that is the classic way of doing problems like that. However, in this case, I'm going to look at settlements, or look at this a little differently in this course, and that's a classic way of doing it, because what basically it assumes is that the soils assume elastically, and then the particles start rearranging themselves, and then stuff starts happening. Well, how does that work? But in some cases, elastic settlement is a good way of computing all the settlement a foundation can be expected to do, and we're going to talk about that with rocks and intermediate geomaterials. There are, now you ask, what are intermediate geomaterials? Is he trying to pull something on us? Well, I'm not trying to pull anything on you, but as is frequently the case, the earth is trying to pull something on you. Just when you think you know everything, the earth comes up with something different. And that's true. Now, we've talked about rocks. We talked about soils. What's an intermediate geomaterial? As you might have guessed, and this comes from the Soils and Foundation Handbook, intermediate geomaterials are transition materials between soils and rocks. The distinction of IGMs from soil rocks for geotechnical engineering purposes is made purely upon the strength of the geomaterials. I'm not going to get too far into IGMs other than to alert you to their existence. We do see them in certain types of foundations, depending upon the stratigraphy. So, for example, a good example of an intermediate geomaterial here would be a very highly weathered rock. I said that we have a lot of weathered rock around here, and a lot of times the rock is either a poor quality rock or a high quality soil. That's an IGM, pretty much. And you can use you can use elastic methods to actually estimate the failures, and your Soils and Foundations Handbook discusses that in Chapter 5, and it does so in fairly extensive detail. This is the equation 819, and by the way, I know we're looking at something that's part of it's in Chapter 5, and part of it's in Chapter 8. One of the things about soil mechanics is that nobody can agree on the batting order of the subject matter. So everybody has a different idea about it, and I have my own idea. This is the general form of the equation for the deflection of a shape under a uniform load in elastic material. And you will, if you were to make the proper substitutions with this equation, is basically the same, applied strictly to a circle, and you should satisfy yourself that for a flexible circle you will get the, if you substitute the C sub D of unity, you will get the same thing. By the way, B sub F is the basic size of it, which for circles is diameters. For rectangles, it's traditionally we say for rectangles it is the shorter of the two sides. For square doesn't make a difference, it's either way. But for rectangles, we traditionally, for customary sake, say it's the shorter of the two sides. L being the longer of the two sides. And basically what you do, instead of going, once you, and if you don't believe me, again, my web piece on this subject goes into a lot of gory detail about the equations underlying this. The equations underlying this are a bear. They're as bad, and in many cases worse, than the equations that you saw that underlying the Fadum chart for rectangular stresses. So what we do is we use this nice little chart here. This chart's been around a long time. Basically for this C sub D. In other words, and I'm going to show you an example of this, which is right here, of elastic settlement in rock. Given the same circular foundations before, now we're going to see it on rock. RMR is equal to 50, and if you want to find out what that's all about, you need to look at the Soils and Foundations Handbook equation 5-29. The E sub S is 145,000 psi, or is equal to 1,000,000 kPa, and the Poisson's ratio is 0.33. The Soils and Foundations Handbook gives you a fairly detailed, detailed treatment about how this is all about, and for a wide variety of rocks. And if your rock quality gets poor, you get into the really poor, gets into me. It also has another another thing which uses rock quality, RQD, and you need to look at both of those. But in any event, deflection at the center, all I do at this point is plug and chug. Actually, I can use the Verroy equation 28.15, the one I presented right there. I can get the same result. That's what I was just referring to with the, and all I do is plug into it. C sub D is unity. Delta P is again 122 kPa. The B sub F is now 25 feet, which is the diameter. Again, Verroy's equations are with radius. Nu is 0.33. E sub S is 1,000,000 kPa. All I do is plug and chug, and I get 0.0027 meters, or in a little more familiar units, 2.7 millimeters, which is not much. Of course, what isn't not much depends entirely upon the structure. We're going to look at this in foundations, but structures, the requirements for limiting deflections and settlements in foundations vary according to the type of structure that it is. What's adjacent to it, how it has to line up with everything else. Sometimes those limits can be very narrow, and sometimes they can be very, very wide. The 60-degree method, or the 2-to-1, is sort of a back of the envelope thing. Basically what it assumes is that it transforms the bulb you see under the Boussinesq theory into a sort of a conical or truncated pyramid shaped type of thing, where you've got where basically the stresses decrease linearly the further you go into the ground. Well, actually, Linearly, not quite. Actually, it's the square of the distance from the surface, because the area increases, the size increases linearly, and with a rectangle or a square, the length of those, you multiply the two increasingly, and you get a square term. So that's what it's all about. It's easy to apply. You can see how that it's done here. The delta P down here is equal to the load on the foundation. Be careful, it's this load, the way they've got this set up, times B plus Z, which is this B plus this Z right here, the Z from here to here, and L plus Z, which is this L plus this Z. And that gives you, and this is a bigger area. In other words, instead of having P is, if we were going to compute the stress at the surface, it would be P over L times B, area of the rectangle. Here, the rectangle we're looking at is bigger further down. For square and circular cross sections, you can simplify it to this equation. Note that little q is the load per unit area. And so they should not be used. 2-to-1 methods are fine to use only if and only if you're interested in the center, what's directly below the center of the foundation, which is, for most engineering applications, is what you're interested in. That's where the maximum stress is. At the center of the foundation, if I use a 25-meter tank, and if I just plug and chug into this equation, I'll get this. It's just plug and chug. 122 is the same unit load over 1 plus 0.4 squared is equal to 62.2 kPa, which is different, but not that much. And in many cases, for many purposes, with the information we have, the 2-to-1 method is accurate enough for our purposes. Because there are a lot of other uncertainties, variations in the stratigraphy, uncertainties in the soil, in the soil properties, particularly effective stress, that would lead us not to get too pushy about this. It's a very useful method. Plus the fact that Boussinesq itself has problems. Boussinesq assumes a isotropic, uniform, elastic, semi-infinite mass around the soil. Usually the semi-infinite part is about the only one that's really with reality. The rest of it, kind of dicey. Okay, combine effective stress and apply point. We remember this problem earlier, you remember that we computed the effective stresses due to just the soil. Now we put we're going to put a foundation on, a 5-foot wide strip footing with a loading intensity of 1,000 psf. Compute the stress increments under the center line of the footing and plot them on the P0 diagram. Now, you ask, how in the... First of all, we've already been through the effective stresses, so there's no doubt about that. But how did you do these? Well, the way they just tabulate it. First of all, they use a chart. Probably use a chart for this. And the way they do it is for every depth they put Z over B. In other words, the depth. So for example, B is the width of the foundation. If at 2.5 feet, Z over B is going to equal to half because the foundation's 5 feet wide. And 5 feet was going to be unity and so on. That's how they get the Z over B. The isobar value is what they're probably doing. And I would strongly suggest you check this for yourself until you get the results you want, or at least line up with theirs. They're probably using this thing for their result. And they're only looking at, let's see, this is a strip load, so we use this side. Infinite long foundation equals to strip load. This. And this is for square foundation. Wait. Yeah, that's right. So we'll use this one. And they're looking strictly under right here. So they're probably doing these isobars, which that's what they call them. And they're figuring out what is the, and from here, if Q is the unit load of this in, say, PSF or whatever, then they're figuring out what the pressure, the stress is under there. Do that. You can also use these equations as well. In fact, Voigt has in the center of the plane, he has this. And I would strongly suggest you would look at that. Take this example and try to compute, use this to compute to an answer, so to speak, since you have the answer in front of you, to compare the charts of strip loads. Let's come back to this now that we've gone through a little detour with the charts and the Voigt equations and all that. We now, with the isobar values, those basically is the influence coefficient. It's no different. And therefore, the delta P is equal to the isobar value, or the influence coefficient, times the stress delta P. Now you say, yeah, and the problem gives you 1,000 PSF is located on the ground surface. One thing you gotta be careful of is that the foundation is that many times these problems will give you a unit load per unit length, but many of the charts are written in unit area load. So, for example, how would this work? Well, if I told you that this had a 5 kip per foot load, how would you do this? Well, the way you do it is you would take the 5 kip per foot, you would divide it by 5 foot of width, and you would get the unit load. That's how easy it is. So, for example, 5 kips, 5,000 pounds, divided by 5 feet is equal to, which is the width, is equal to 1,000 PSF. So that's how you get to that. In any event, what you're going to end up with, your goal for each point, is to whether you use Voigt's equations, whether you use their isobars, or whatever you do, the point is right here. This is the additional stress that foundation induces in the soil. At the surface, it's 1,000 PSF, just as a spoiler alert. And then it goes down from there. Notice that the deeper you go, the lower, down to the point you get to 20 feet below the surface, and you're down to a stress change of 160 PSF. And that makes sense. So, the original effective stresses are right here, and these are computed in exactly the same way that you compute the, they are computed in exactly the same way as you compute the effective stresses earlier. The only difference is they did it for more points. Instead of doing it just a few, they did it for a lot of them. And then the total stress at the end of this loading on the foundation is this plus this gets to that, that plus that is that, that plus that is that, which is actually illustrated by the column heading. The feds don't like to leave anything to the imagination. So they have the total stress at the end is equal to the original effective stress plus the delta P from the foundation. And then they plot all this. And you'll note that as this goes, now this here is equal to this to start with. The difference between the two is right here. And you'll notice that as you get deeper in, the impact this has on the effect on the stresses is less and less and less. Now you say, well, why would you care about what happens way down there? Well, it depends on what is way down there. That's what it would depend on. It depends entirely upon the, if you've got, for example, in this case, you've got pretty much uniform soil conditions. Nobody is, and probably, unless, it's not, by the time you get down into the water table, the difference between the two stresses here to there is much smaller. In fact, it goes from 800 to the water table is 320. At 800 at 0.25 feet or 3 inches. It's that way. Whereas in 320, so it's not that much. However, and this is what we're going to find out in consolidation, if you've got a soft layer down there, I mean, uniform stratigraphies are not common and should not be expected. And if you've got a soft layer down there and it's likely to compress, your interest in that, what's going on down there, is a lot greater than it is if you know you've got uniform stratigraphy or reasonably uniform stratigraphy. And we're going to see why the solution to that was one of the major advances in soil mechanics. So that, in a nutshell, is how you combine stresses using this example. So that concludes our foray into using theory of elasticity to estimate stresses and to estimate deflections. I have an entire piece on how these equations come about, how they're used, both, and it gives with some interesting illustrations, and I would suggest you look at those. But in any event, until next time, thanks for watching, and God bless.